All right, so today's lesson is going to cover graphing square root functions. I'm going to break this lesson up into two pieces. So today we'll talk about graphing square root functions and the pattern involved, and tomorrow we'll talk about graphing cube root functions. So when we talk about graphing functions with roots, we know that this first example, y equals the square root of x, or y equals 1/2 x. So this fraction exponent, it's called a rational exponent. So if I take something to the power of 1/2, that actually means I'm taking the square root of it, okay? So I'm going to slide over to the left a little bit, and we're going to talk about the pattern of a square root function. So let's just make a table really fast. Make a table of values. So I cannot take the square root of a negative number because we can't graph anything that's imaginary. So let's start with 0. When x is 0, the square root of 0 is, well, 0. When x is 1, the square root of 1 is 1. And I'm only going to put perfect squares in my table because I don't want to try to graph approximations. So when x is 4, the square root of 4 is 2. When x is 9, 9 is a perfect square. The square root of 9 is 3. And if my graph went all the way out to 16 on the x values, I know that the square root of 16 is 4. So I'm going to go ahead and plot my ordered pairs. When x is 0, y is 0. When x is 1, let's see, the square root of 1 is 1. The square root of 4 is 2, so that's the ordered pair 4, 2. And the square root of 9 is 3. So the square root function makes a graph something like that, okay? So I want to talk about this. I want to talk about the pattern. So we're starting at the origin, right? We're starting at the origin, and that's the ordered pair 0, 0. So if I move 1 unit to the right, well, what is the square root of 1? I go up 1. If I move 4 units to the right, what's the square root of 4? Well, that's up 2. And if I move 9 units to the right, what's the square root of 9? Well, that's up 3. So that's my pattern. Remember, once you figure out what your pattern is, you multiply that by your a value. Remember, a is the leading coefficient inside of your function, like the coefficient that leads your function, okay? Let's talk about the domain. Well, remember that your domain is your x values. Domain stands for the x values. And if I look at my graph and at my table, I see that there are no x values that are less than 0. Everything is greater than or equal to 0, right? Because remember, x can't be negative. So my domain, well, that just means that x is greater than or equal to 0. And if I want to write that in set or interval notation, let's see, I'm including the 0, and it goes all the way up to positive infinity. Okay, so that's interval notation. Well, what about the range? The range is the y value. Range stands for the y values. And I also notice with my range that my y values are also greater than or equal to 0. So y is greater than or equal to 0. So same kind of idea with interval notation. 0 all the way up to positive infinity. Remember, the bracket means that it's included. The parenthesis means it's not included. Okay. So at the bottom of your notes, again, we're not going to focus on cube roots today. At the bottom of your notes, it says, how does the rate of change for a square root parent function change? Like, how does it compare to other functions? Well, the rate of change is slower. I'm just going to write the rate of change is slower, right? Because you're taking the square root of a number. Instead of growing by a square or a cube, you're taking the root of it. All right, so we're going to talk about transformations, and I'm only going to focus on the ones that are the square root function. So if I look at this f of x, this is referring to the square root. These two right here are actually cube root functions. I don't know if you see that, cube root. But the movement is still the same. So we're still going to talk about the transformations because this transformation applies to any function, not just square root functions, right? This applies to any function. Okay. So let's see. If I have the square root or the cube root of a number, or if I have a function, right? This is the function that we're talking about, and I add 5, that just means that the whole graph, the entire thing, is moved up 5 units. So it's a vertical movement up 5 units. If I have a -8 outside of the function, even though it's a cube root, I'm just talking about the transformations, that means that it's going to be moved down 8 units. Okay. Notice that I have a +2 inside the function, f of x plus c. So the function is, the plus is coming inside of the function. Well, you should remember this from parabolas. If I add 2, like if I have x plus 2, I know that my root is actually -2, right? That means that I move to the left. So if it's plus, you actually move left. If it's minus, you actually move right. So I'm going to move to the left 2 units. So the minus, just like we said, that means that we're going to move to the right 9 units. And then if I have a negative outside of my function, that just means that my function is going to reflect over the x-axis. This is going to be a reflection over the x-axis. Okay, so we're going to do example 1 and 3. Example 1 and 3. So we're going to compare the graph of g of x to the graph of f of x, but we're not really using Desmos. We're just going to talk about what happens. Okay, so I just learned that if I have a plus or a minus outside of the function, that moves me vertically, right? That's a vertical movement. If it's minus, if it's a subtraction sign, I move down. So what is happening to this graph? Well, it's moving down 3 units. Moves down 3 units. Okay, let's look at example number 3. So example number 3 has a plus on the inside. Well, if I plus on the inside, I move left, and a plus on the outside up. So this is going to move left 7 units and up 9 units. Left 7 and up 9. Okay, so we're going to look at example 4. It says graph the function and state the domain and the range. Well, remember that this started at the ordered pair 0, 0, right? That's where we originally started at the origin. But this means that I'm moving to the right 1. So I'm going to have to add 1 to my x-axis, and I'm moving up 5. That means I have to add 5. So the origin, or the vertex, if you will, HK, where I begin, is actually going to change from 0, 0 to the ordered pair 1, 5. It's going to change from 0, 0, my starting point, right? So these change the starting point. My starting point was originally 0, 0, but I'm going to move up 5. That changes my y, and I'm going to move to the right 1. That changes my x value. So that is my new starting point, 1, 5. And I see that I have this -2 out in front of it. That means that A is -2. So I'm going to write down my pattern. I remember if I move 1 unit to the right of the origin, I go up 1. If I move 4 units to the right of the origin, I go up 2. And if I move 9 units to the right of the origin, I go up 3. But A is -2. So that means that each one of these numbers has to get multiplied by -2. And when I do that, that means I'm actually going to go down 2, down 4, and down 6. So let's see. When I move 1 unit to the right of the origin, the starting point, I actually am going to go down 2. If I move 2, 3, 4 units to the right of the origin, I'm going to go down 1, 2, 3, 4. And if I move 9 units to the right of the origin, I actually am going to go down 6. 1, 2, 3, 4, 5, 6. So we're using patterns, again, just like we did with quadratic functions or parabolas, to graph our square root function. Okay, we will do example 4b tomorrow. Not true. We're going to do example 4b now. I'm skipping 5a and 5b. My bad. So let's look at example 4b. Okay, so I have a movement outside of the function. That means that I'm going to go down 8. That's my vertical. So my original starting point was 0, 0. But since I'm going down 8, my new starting point, right? The new starting point is the ordered pair 0, -8. So I'm going to plot that point first. 0, -8. Okay. This is my A value. A is 1/2. So let's talk about my pattern. If I move 1 unit to the right of the origin, I go up 1. If I move 4 units to the right, let's see, the square root of 4 is 2. If I move 9 units to the right, the square root of 9 is 3. But each one of these values has to get multiplied by A, which is 1/2. So instead of going up 1, I'm only going to go up 1/2. Instead of going up 2, I'm going to go up 1. And instead of going up 3, I'm going to go up 1.5. So again, I'm going to move 1 unit to the right, and I'm going to go up 1/2. I'm going to move 2 units to the right, up 1, and not 2 units to the right. My goodness, 4 units to the right. Sorry. 1, 2, 3, 4 units to the right, up 1. And when I go 1, 2, 3, 4, 5, 6, 7, 8, 9 units to the right, I go up 1.5. So this is what my square root function looks like now. Okay, so I'm going to shrink these up just a little bit so we can talk about the domain and the range of each function. So let's go back to 4a. So my domain, that's my x values. Well, I noticed that the largest, the highest is like infinity, right? It's going to go on forever. But the smallest x value is 1. So all x's are greater than or equal to 1. And I know that from my starting point. I start at 1. If I would put that into interval notation, I'm going to use a bracket, 1, comma, positive infinity. Let's talk about my range. Well, my range, those are my y values. My highest y value is 5. 5 is my starting point, but it's reflected. That negative means it's reflected. So the highest value is going to be 5. And everything else is going to be smaller than that. So I actually am going to go all the way down to negative infinity. So that's going to come first. 5 is the highest point. 5 is the highest point. So 5 is the largest number in my interval. Let's do it again for the second graph 4b, or function 4b. So let's see, my x value begins at 0 again. So x is greater than or equal to 0. Oops, I'm going to do it. Bracket 0, comma, positive infinity. My range, however, my y is -8. Y is going to be greater than or equal to -8. So interval notation, -8, comma, positive infinity. Okay. All right. So we're going to skip the 5a, 5b, and I'm going to do example 6, not example 7, just example 6. So example 6 says, hey, look at the graph and tell me what the function is. Well, I know that this is a square root function. I know it's a square root function. So I'm going to say f of x equals something, and I'm going to put a square root sign there. So let's see. The origin typically I start at the origin 0, 0, and I'm starting 1, 2, 3, 4, 5, 6 units to the left. Well, if I move to the left, that means I actually add plus 6. So that's going to look like x plus 6 on the inside. Let's see. If I have a new starting point and I go to the right 1, up 1, do I hit those? Am I still on the graph? If I go to the right 4, up 2, does the pattern still fit? To the right 9, up 3, yes. So there's no vertical movement and there's no stretch. There's no number outside the function, meaning there's no a value. Okay. So this is what my function is. Y equals, or f of x equals the square root of x plus 6. The domain, well, that's my x values. X is greater than or equal to negative 6. So bracket negative 6, comma, positive infinity. And my domain, or my range, y values, y is greater than or equal to 0, 0, comma, positive infinity. Okay. All right. Again, I'm skipping number 7. We're going to talk about this idea right here. It says, let's consider the domain of a square root function without looking at a graph. Okay. So we know that we can't take the square root of a negative number. So if I start with the function f of x equals x minus 4, what does that mean? If this cannot equal a negative number, well, that just means that x minus 4 has to be what? Well, let's see. If x minus 4 can't be negative, that means it has to be positive, right? If it can't be negative, that means it's got to be positive. Or it could be 0, right? It could also equal 0 because we can take the square root of 0. So what do we say about numbers that are positive or 0? Well, we just say that they have to be greater than or equal to 0, right? So what does that mean? That means that the idea, the function or the expression underneath the square root has to be greater than or equal to 0. So you can actually solve for the domain by setting the value that's in the radicand. And that word radicand, that just means the stuff that's under the radical symbol. That's what the radicand is. Okay. So this, you set it equal to, or you say that it's got to be greater than or equal to 0. And then you solve it. So if I were to solve this inequality, I would add 4 to both sides. And that means that x, my domain, has to be greater than or equal to 0. This is my domain. My domain, x is greater than or equal to 4. I think I said 0. X is greater than or equal to 4. And if I want to write it in interval notation, 4, comma, positive infinity. Okay, so we're going to use that same idea. We're going to set the radicand. We're going to say that the radicand has to be greater than or equal to 0. So let's see. I would subtract 5 from both sides. I'm just solving this inequality. That gives me 2x is greater than or equal to negative 5. I would divide both sides by 2. And that means that x is greater than or equal to 5 halves. This is my domain. X is greater than or equal to 5 halves. If I want to write it as an interval, I write negative 5 halves, comma, positive infinity. So my domain, x is greater than or equal to negative 5 halves. In my second example, example number 9, same thing. We have a fraction in the radicand, but it still works the same way. Hopefully you remember how to get rid of a fractional coefficient. So x has to be greater than or equal to 0. Let's see, I'm going to add 8 to both sides. That gives me 2/3 x is greater than or equal to 8. 2/3 x is greater than or equal to 8. To get rid of that, I multiply by the reciprocal, multiply both sides by the reciprocal. That means that x is greater than or equal to 8 times 3 is 24, divided by 2 is 12. So my domain, x is greater than or equal to 12, and in interval notation, 12, comma, positive infinity. Okay, so we're going to jump to the practice, and I'm going to talk about the questions that I want you to do for today. So for homework today, you're going to do 1, 2, 3, you're going to do this problem, and let's say 4 and 6. 4 and 6. We'll save the rest for tomorrow, okay?